Hello everyone. In this video we are going to discuss the BMath 2008 problem number 5. So as you can see here that the problem says that if a polynomial p with integer coefficients has 3 distinct roots or 3 distinct zeros, then show that Pn is not equals to 1 for any integer n. Okay, so what do you mean by that? So this was very easy problem, and you just need to know that I mean some properties of the integers. So let's proceed. So the thing is, p is a polynomial with integer coefficient, so that's the main thing about this problem. So suppose you have px, the polynomial, and it has 3 distinct zeros. So let there be a, b, c. So x minus a times x minus b times x minus c times some q of x. Okay, now I don't know the degree of the polynomial, so yeah, so whatever remains is q of x. And now if you just simply what do we would do? We would just go with the help of contradiction. So let there exist n in the set of all natural numbers, or they have said integers. So show that Pn is not equals to n for any integer n. So okay, let's take n to be any integer. So there exists n in Z such that P of n is equals to 1. So this is the way of contradiction, that is, we assume this and then we will show some contradiction, and thus this is our hypothesis, and so it will be wrong. So then P of n, which is equals to n times a times n minus b, n minus a times n minus b times n minus c, n minus c times q of n, and this is equal to 1. Okay, and now you can very well see that these three are distinct integers, because a, b and c are given to be distinct integers. So n minus a, n minus b and n minus c will be distinct, and thus we get that 3 distinct integers are dividing 1. Okay, and that can't happen because 3 distinct integers are dividing are dividing 1, and that cannot happen because 1 can have at most 2 factors or 2 divisors, that is plus 1 or minus 1, and that's a contradiction. So this was a very easy problem, and thus this was our hypothesis, and so it's wrong. That is, our hypothesis was saying that there is some integer n such that P of n is equals to 1, but now we see that proceeding with that we got a contradiction, and thus our hypothesis is wrong, and thus proving that there exists no integer n such that P of n is equals to 1. Okay, so that's it for this video. Thank you for watching. See you in the next one.